Hello, ladies and gentlemen. We are going to learn about related rates. They are a very challenging topic at times. The biggest key to solving a problem that has dealing with related rates is figuring out what formula you need, bringing in everything from your past math classes. A lot of times it's from a geometry class. And realizing how it is incorporated into calculus. So I have here on your notes sheet kind of a guide to help you figure out a way to set up the problem so that you have a good understanding of all of the information that the problem's giving you, what you don't know, and what you need to find. So let us begin. We are going to begin with this problem here that has a pebble being dropped into water, causing ripples to form in circles. Now this diagram, I would always start off drawing a diagram. This diagram is actually not extremely helpful. Basically, you're dropping in a pebble and the circles are getting larger and larger. Forgive me if my circles don't look very much like circles, like that one right there. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, so when the radius, if I had an actual circle here, if the radius itself is 4 feet, we want to know at what rate is the total area of the disturbed water changing. So these problems, we have to come and incorporate some kind of formula, usually, again, like I said, is a geometric formula. And what we are going to do is find the rate of change of all of the variables in the formula with respect to time. It's very much like implicit differentiation where we were respecting x. However, since it's dealing with real life situations and we're trying to find the rate of change versus time, we are not going to have dx anymore. We're going to have over dt. So what is given to us is that the radius is changing at a rate of 1 foot per second. So in this problem, that is actually what we are given. So the change, which is always d and your variable, we're going to say our radius is a little r. So our dr over dt is 1 foot per second. That is given to us in the problem. What we are trying to find is the rate, so that means it's some kind of change in the total area. And so what we need to find then is the change in area with respect to the time that we have. So we need to find dA over dt, and we want to do that exactly when our radius is equal to 4 feet. So what we need to start out is figure out how is there and what kind of formula, how is there a way for us to connect a radius with an area, and we are having circles, so hopefully this is a fairly basic formula here. Hopefully you all remember that area of a circle is equal to pi r squared. Once we have our formula, what we want to do is find the instantaneous rate with dealing with this formula. So we would like to find the derivative of this equation. Now remember, it is with respect to time, so it's very similar to implicit differentiation, where we are trying to find the change in our area with respect to time. Now, when I go to find the derivative of pi r squared, we're going to follow our normal derivative rule. So we're going to have a power rule here. So 2 pi r. However, r is not the variable that we are respecting. It's just like having a y in implicit differentiation. We have to throw in then, in implicit, we would throw in dy over dx. But here we're respecting time, and r is not time, obviously. So then I'm going to have a dr over dt. At this point in time, we want to fill in what we know and what is given to us in the problem. We don't know dA over dt. That is what we are trying to find. So that's going to remain dA over dt. I'm going to have 2 pi. I would like to find the change in the area specifically when our radius is 4, and our problem is telling us that our radius is changing at a rate of 1 foot per second. At this point in time, we have all numbers, and we will be able to find that our change in our area at exactly 4 seconds is going to be 8 pi feet per second. Now keep in mind this is going to be 4 feet per second, so we're going to have change in area is going to be, we have 8 pi feet per second. Sorry for that little delay there. Our, I missed this feet in here. Let's get this working here. Here we go. We have a radius of 4 feet. There we go. So when we multiply 4 feet times 1 foot per second, we actually end up with feet squared per second, and that should make sense because we are changing an area. Area is squared, so we have 4 feet squared, or 8 pi feet squared per second. And we now know our change in area. And we are done with this problem. So, moving forward to another example, the best thing with related rates is to literally just practice, because I often find that the hardest part about solving these problems is just setting them up and figuring out where to even begin. So, let's read this problem. This one says we have a ladder that is 6 meters long that is leaning against a house. The base of the ladder is being pulled away from the house at a rate of 0.5 meters per second. How fast is the top of the ladder moving down the wall when the top of the ladder reaches 5 meters up the wall? So to give us an idea of what's going on, we really need to have a diagram in this case. So here's my house. I'm sure it's going to be a beautiful house here. Here's our house. And what we have, let's change some colors and make this exciting. We have a ladder that is leaning against a house. And what we know is that that ladder is 6 meters. So that is one thing that is given to us. We have a ladder that is going to be 6 meters. Basically, what we also know is we have a ladder that is actually being pulled away from the house. So the ladder is going to form a right triangle with the house. Hopefully right now you're kind of thinking what kind of equation we're going to need. But this ladder right now is being pulled away from the house in this direction at 0.5 meters per second. So obviously that is some kind of rate of change. What we want to know is how fast is the ladder moving down the wall. So I want to know this rate of change that I'm drawing right here in blue. So what we have is a right triangle. We have, and we want to know that's happening exactly when this ladder is actually 5 feet up on the wall. So right now we have a right triangle, and hopefully you realize that the equation that we're going to use to incorporate the ladder, the side of the wall, and what's moving along the ground is actually the Pythagorean theorem. So we have a squared plus b squared equals c squared is going to be our formula that we're going to use. Now I'm going to come over here and I'm going to label each of these sides so we have an idea of what's going on. Basically we have, I'm going to label this side A, this side is going to be B, and our hypotenuse obviously is C. So the other piece of information that we are given, basically then this 6 meters is going to be C. And the other piece of information that we know is that dB, the change in our base there along the ground, is going to be 0.5 meters per second. Now, oftentimes you have to really think about this one. It's going to be a positive meters per, or 0.5 meters per second, because the ladder is being pulled away from the wall. So that side length, this side length right here, this B, is actually getting larger. So it's going to be increasing. We need to have it be positive. What we want to find is this rate of change. So what we want to find is dA over dt, when specifically A is 5. Now, we have our formula, a squared plus b squared equals c squared. We're going to find the derivative of that, so it tells us our rates. So we are going to have 2a. Now, a, again, is not time, so I'm going to have that change in time with respect to, change in a with respect to time. We are going to add on to that a 2b times dB over dt, the change in our base there with respect to time, equals 2c dc over dt. Pretty much any variable you have there, then you're going to have a d and then the variable over dt. At this point in time, I'm actually going to make this a little bit nicer. If you notice, all of them are divisible by 2, so we're just going to stick with this, and we're going to divide everything by 2. And I am going to have a little bit, whoops, that's not supposed to be an equals. Here we go. Plus b dB over dt equals c dc over dt. At this point in time, we are ready to rock and roll and figure out, basically fill in the pieces to the puzzle. Remember, we are trying to solve for dA over dt, so we are trying to solve for this right here. All right. Do we know A? Yes, we know. We want to find this exactly when A is 5. I don't know dA over dt. I'm going to add on to this B. Now, at this moment in time, we're going to leave that blank because we don't know B yet. There's going to be a way we can find it. dB over dt is given to us in, oh, why am I writing dB over dt? Is given to us in the problem. So I need to go and input then 0.5 meters per second equals C, which is going to be, now C is basically our ladder, and our ladder is 6 meters, and dC over dt is the change in the length of the ladder. Well, logic and common sense is going to tell us that our ladder is not changing its size. Our ladder will always be 6 meters, so this dC over dt is actually going to be 0. So that's kind of something that you're going to have to intuitively think about in the problem. Now, we are trying to solve for this dA over dt, but in order to do that, I need to find what B is. Now, again, we're going to go off to the side here, because essentially what we have is a right triangle. Ooh, that's not really a good right triangle. Sorry about that. We have a right triangle with a hypotenuse of 6, and we have a right triangle specifically when this leg over here is 5. Now, we are going to have to do a little bit of math and realize that when this leg is 5, what is the length of this second leg? And that we are actually going to fully use the Pythagorean Theorem. I'm going to have 6 squared minus 5 squared is basically going to be b squared. So basically I have b is going to be the square root of 11. So I'm going to come down here after I figured that out, and for b I'm going to have the square root of 11. Okay. At this point in time, we have everything that we need to know so that we can actually now solve for dA over dt. We end up with 5 dA over dt plus 5 square roots of 11 equals 0. So I have 5 dA over dt equals a negative 5 square roots of 11. Let's make this bigger. And divide by 5 on both sides. So I end up with negative the square root of 11, which is roughly negative 3.31. Let's try that again. Negative 3.31. Now, it's negative. And hopefully that should maybe make some sense. And that is because we are trying to find the rate at which this distance here is changing. And it started off at a larger number and it's going to get smaller as we pull the ladder away from the wall. The distance here from the ladder up high is going to be getting shorter. So it should make sense that our change in that length is going to be negative. So I sincerely apologize here. I can't even read my own writing on my notes, guys. We have, this is actually 0.5. I was thinking that was the times. So we actually have half of the square root of 11. Oops. Here, let's try this again. That's 0.5. Basically, we are a tenth of what I thought we were, so that's going to be 0.5. And we are going to end up with 0.331, not 3.31. I apologize, I can't read my own writing here. 0.331. But it is still negative. It is going to be decreasing. The side length is getting smaller. All right, on to our next example here. We have a cone. Come on. There we go. All right, we have a cone. Water is going to be flowing into a cone that has a height of 16 centimeters and a radius of 4 centimeters. And the water is flowing into the cone at a rate of 2 centimeters cubed per minute. How fast is the water level rising when it is 5 centimeters deep? So we are given, ooh, this is going to be tough to draw here. So, oops. We are given a cone and that's a horrible cone. But we are given a cone that has a height of, let's just draw a little triangle over here so you can see what's going on. We have a height of 16 and a radius of 4, and this is in centimeters. We want to know how fast is the water level rising when it is 5 centimeters deep. And we are given the rate at which the water is coming in. So basically, we are given the change in the volume of the water, the amount of water that is coming into the cone. So we are given the change in the volume, and that is going to be 2 centimeters cubed per minute. And what we want to find is how fast is the water level rising? So how fast is this filling up? Well, that's all in terms of the height of the cone, the height of the water inside the cone. So what I don't know is dH over dt. And we want to know this specifically when the height is 5 centimeters tall. Now, our volume is going to be represented by the volume of a cone, and yes, you are going to need to know these and remember them from before. The volume of a cone is 1/3 pi r squared h. Okay. Now, if you think about us immediately going and taking the derivative, hopefully you recognize that r times h results in a product rule. In a product rule, since we are respecting time, at some point in time, we would have dr over dt times dh over dt. And are we given anything in terms of what dr is? We're trying to find dh over dt. We have, at this point in time, no way to find what dr over dt is. So we have to find that. What I suggest doing in this case when we have to make a substitution is come over here off to the side and realize that if we had a full cone, we would have a height of 16 and we would have a radius of 4. We want this to happen specifically when we have a height of 5 and we don't know the radius yet, but that's okay, we'll figure this out. But basically, this triangle that we get at any point in time wherever the water is in this cone, we are actually creating two similar triangles. Again, we're bringing lots of geometry into this. We have two similar triangles. So essentially, this is going to be the height of whatever we are instantaneous at any point in time times your radius. This creates similar triangles, so hopefully you guys remember that h over 16 is going to be proportional to r over 4. Knowing this, we realize that if we cross multiply, we have 4h equals 16r. Divide by 4, so h is equal to 4r. This gives us a relationship between h and r. Now, there's no way for me to find out what the rate of r is. We're trying to find out what dh is. So my goal is going to be to not have r in this equation, so I don't even have to worry about what dr over dt is. So I'm going to substitute for r. R is going to be, if I use this proportion over here, 4 over, oops, let's try that again. R is going to be h over 4. H over 4. So I come back before I even find the derivative, and I'm going to make a substitution here, and I'm going to say R is going to be the proportion of h over 4 squared times h, which really means that our volume formula for this cone specifically is going to be 1/3 pi h cubed over 4 squared is going to be 16, so I'm going to have over 16. Now I am ready to go and find a derivative, and this is a much easier equation. I don't have to worry about product rule. That's another good thing that we have if we make this substitution first. We're going to have dv over dt equals, this is just a power rule. Bring down the 3, 1/3 times 3 actually is gone, so I have pi h squared over the 16. And dh over dt, since height is not time, we have to respect the time. At this point in time, we can fill in what we know. Our change in volume is 2 centimeters cubed per minute. I have pi. I would like to find this specifically when my height is 5, so I'm going to have 5 squared over 16 equals dh over dt. At this point in time, let's solve for this dh over dt. We are going to have multiplied by the reciprocal to get to the other side. So we have 2 times 16 over pi times 25, 5 squared. I actually put this in my calculator, and I get a rough estimate that we are going to have a change in our height of 0.407. Now, sometimes I don't mind if you guys don't carry the units through the whole problem. I know in some of your science classes you have, but if you take a look at the end and figure out what's going on, our change in our height is going to be one dimension. So it's not going to be centimeters cubed or centimeters square. It's one dimension, centimeters over, and in this problem we are talking about minutes. So we know that our height is changing at 0.407 centimeters per minute. And I'd like you guys to round to the nearest thousandth, so 3 decimal points is good. And we just finished a third related rates problem.